So happily, I can see some faces on the screen, so I don't feel like I'm completely talking to myself. And normally in our ESR meetings, we have to keep a sharp eye on the time so that Thomas's dinner doesn't get cold. And even though Thomas isn't with us tonight, I feel we should hold to tradition and try and move it along and be done reasonably soon. I'll go to the next slide. The sources for this talk are the Ministry for the Environment Greenhouse Gas Inventory, and I may not be quite up to date with the latest one, and the Climate Change Commission's draft advice for consultation. And the main thing is Chapter 8 and Chapter 6 of what I will loosely refer to as Assessment Report 5, so Climate Change 13, the physical science basis, and the contribution of Working Group I. And kind of lurking in the background will be William Ruderman's excellent book about how humans and climate change together, called Ploughs, Plagues and Petroleum. And so this is the title page of Assessment Report 5, Chapter 8, and you can see there's quite a lot of people there, and I'm sure they're all well qualified, and I take this to be as the gospel truth, or as near as we can reasonably get to it at this time. And why did I do this? Well, start with why, which is the last thing. The methane metrics that we are presented with kind of seemed unsatisfactory, and I'll go into more reasons for that. These are my opinions, and although I've centred around the ESR committee, not necessarily everyone in ESR agrees. And my employer is supportive. That's me and my partner, but again, it's not a company policy or anything. And maybe the main thing is that this is nothing new in a way. It's just a change of perspective, and it's based on that published science. And I would point out that when a problem seems intractable, then changing the perspective is one of the methods of transition engineering and can be very helpful. Okay, so going on to methane metrics, and this is figure 828 of Assessment Report 5. And the red curve that you see there with the red cross-hatching is of interest to us. It's fairly close to methane. It's a hypothetical greenhouse gas with a 13-year lifetime, according to the caption of the figure. And it expresses the effect of a pulse of gas, let's say 100 tonnes of methane that you put up into the atmosphere on day one of your experiment. And the radiative forcing, and we'll talk at some length about radiative forcing, this is a talk done by a layman and for laymen really. The radiative forcing decreases because the mass of gas decreases. Methane has a relatively short lifetime in the atmosphere. And the next part B of the figure is the global temperature potential, and we'll talk a bit more about that later too. And so these are standard metrics as set out in Assessment Report 5. And the absolute global warming potential of component I over time horizon H is the integral of the area under the curve, so the integral of the radiative forcing with time. So that's just what I've said there, written it by hand. And absolute global warming potential is in watts per square metre, years per kilogram. So it's a watts, it's a power multiplied by a time. And so it has a straightforward interpretation. It's an energy input to the Earth atmosphere system per square metre of Earth's surface area per kilogram of gas, and over time H you integrate it over a given time horizon. And according to assessment report 5, the current best estimates are that GWP 20, so global warming potential over 20 years is 84, and over 100 years it's 28. And so some things about that is, one thing is that H, the time horizon, is arbitrary. And assessment report 5 says there is no justification for selecting 100 years. And when we think about the urgency of the climate crisis, wouldn't maybe GWP 20 be more relevant? On the other hand, maybe it would put unfair emphasis on methane emissions. And there's one more thing which I feel should be pointed out, and that's that for most of our New Zealand methane emissions, there's no fossil carbon involved. So you have carbon dioxide in the atmosphere, turns into grass by photosynthesis, goes into a ruminant. Methane is produced in the symbiotic process with the methane-forming bacteria. And then in due course, that CH4 methane that goes into the atmosphere is oxidized to carbon dioxide. And that whole thing, in a way, is just the modern carbon cycle. So that's well, we'll look a bit more about that later. But on the GWP 100 measure, where methane emissions are thought to be 25 in the previous assessment report, or 28 in this assessment report, times carbon dioxide, then methane is considered to account for about half of our New Zealand greenhouse gas emissions. And so maybe just to complete some stuff on the methane metrics, global temperature potential is the change in temperature at a particular time of component I divided by the change in temperature due to CO2 at that time. And it's very straightforward to interpret, of course, but it's subject to quite high uncertainty in calculation. From my kind of engineering perspective, I like the energy, the summation of energy, which is global warming potential. I feel once you start saying it's going to lead to a certain temperature change, even from my layman's perspective, I think, yes, that does start to sound pretty uncertain. And both of these metrics are based on a pulse emission of an equal mass of component I and carbon dioxide, both GWP and global temperature potential. And the focus is on emissions and not on atmospheric concentration. So what I propose for an alternative change of perspective goes kind of like this. The rate of emission of methane controls the mass of gas in the atmosphere. And the mass of methane in the atmosphere has equivalent greenhouse effect to X years of emissions of CO2. So when you emit the long-lived gases, that's a measure of how much worse the situation is becoming over time. On the other hand, methane, you put it in the atmosphere and you keep it up there by continuing to emit methane. I'll probably labour that point a bit more. And this, I feel that an alternative perspective on methane would be relevant in New Zealand because of our particular emissions profile. So worldwide, methane is important, but in New Zealand, it's very important. And I think I can also show that the mass of methane that we maintain in the atmosphere by our New Zealand emissions can be calculated. And I think this is quite straightforward. And I'll have a rough go at it in this talk. So what I suggest in a way is that instead of thinking of our emissions profile, when we're thinking about methane, it would be helpful to think of our radiative forcing profile. And this is another figure from Assessment Report 5, and I think it's very helpful in setting out how the thing works. So we have emissions of the greenhouse gases, and those lead to atmospheric concentrations. And those atmospheric concentrations lead to radiative forcing. And that radiative forcing leads to climate change with all its attendant impacts. So carbon dioxide emissions more or less stay in the atmosphere, but Chapter 6 of Assessment Report 5 explains that actually there's a whole range of mechanisms by which carbon dioxide is removed from the atmosphere over a whole range of timescales. One example is the leaves in the Northern Hemisphere. You can see the CO2 concentration go up and down with the seasons. But for rough engineering purposes, you can say that carbon dioxide, you put it up there and it stays up there. It continues to be effective as a greenhouse gas. On the other hand, methane emissions gradually disappear with a lifetime of 12.4 years, according to the Assessment Report 5. And lifetime is roughly like a half-life. We'll have a bit more detail on that shortly. And that's the fundamental problem in comparing emissions of the two gases. You can't really compare eggs with eggs, apples with apples. So radiative forcing, what is it? Well, viewed from the sun, the Earth looks like a little disk, 6,350 kilometres of radius. And solar radiation impinges on that disk at 1360 watts per square metre. On average, fluctuates a bit over the year because the orbit isn't quite round. But for us that live on the Earth, it's not a disk but a ball with a thin layer of gas clinging to the surface. The incoming radiation at the top of the atmosphere per unit surface area of the Earth is 1360 divided by 4 pi r squared over pi r squared, so 340 watts per square metre of Earth's surface area. And energy comes in at those 340 watts per square metre. It has to go back out at 340 watts per square metre because energy is not created or destroyed. Otherwise, we get hotter. But we are getting hotter, and that's radiative forcing, roughly. So the definitions of radiative forcing from Assessment Report 5, they prefer effective radiative forcing, and that is the change in net downward radiative flux at the top of atmosphere after allowing for atmospheric temperatures, water vapour, clouds and land albedo to adjust with global mean surface temperature or ocean and sea ice conditions unchanged. Calculations in this chapter use the fixed ocean conditions method. And radiative forcing is a bit less sophisticated because it only allows the stratospheric atmospheric temperatures to adjust to radiative equilibrium. And the idea is that effective radiative forcing includes both the effects of the forcing agent itself and the rapid adjustments to that agent. In my interpretation, rough layman's interpretation is that one adjustment is that the atmosphere gets warmer. And when AR5 talks about radiative forcing, they are talking about a difference in radiative forcing compared with 1750. So it's assumed that in 1750, at the start of the serious coal burning era, radiative equilibrium prevailed and at a somewhat lower global mean temperature than we have today. And the best perspective on that comes from Flowers, Plagues and Petroleum, I think. It's a very nicely written, readable book. In the long term, of course, radiative equilibrium must prevail. But with more greenhouse gas, it will do so at a higher temperature of the Earth atmosphere system. And total anthropogenic radiative forcing over the industrial era is currently estimated to be 2.3 watts per square metre, with quite wide error bands, as noted there, 1.1 to 3.3. But that radiative forcing is the direct cause of global warming. So for some energy comparisons, 340 watts per square metre comes in, and we at present have an imbalance of 2.3 watts per square metre. So about 0.7% of the incoming radiation is the amount by which the Earth is increasing in energy content. And the world primary energy supply, so this means where civilization gets its energy from, in 2018 was about 14,000 megatons of oil equivalent. And when you convert that into respectable units, it's 5.86 times 10 to the 20 joules. So if you average the world primary energy supply over the Earth's surface area, you get 0.037 watts per square metre, or about 1/9,000th of the incoming solar radiation. And so the comparison that's often given is that the sun shines more energy on the Earth in 1 hour than civilization uses in 1 year. And that happily confirms my calculation, since there's 8,766 days in an average year. In radiative forcing, in relation to world primary energy supply, well, it's about 62 times as much as the world primary energy supply. So those 0.037 watts per square metre that we are releasing by burning fossil fuels is not hugely significant, but it's not, I mean, it's more than 1%. And that this imbalance that we've got, the 2.3 watts per square metre, that was achieved purely by adjusting the atmospheric composition. So I like to think that those of us that grew up fixing our own cars have the best perspective on global warming, because when the thermostat went bung, things went bad pretty fast. And in my river engineering practice, I'm frequently asked to design for RCP 8.5 in 2080 to 2100. And that means 8.5 watts per square metre of radiative forcing. And that's about roughly 4 times what we've got now. And I think, ouch. And as one of my colleagues says, the council building will be flooded. And this is kind of a digression, but there's been an awful lot of words and no pictures. And so I thought we'd got to have one picture. And this is from the International Energy Agency, and it shows where the energy that runs civilization comes from, and up to 2018. And the great bulk of it comes from coal, oil and gas, natural gas. There's a bit of biofuels and waste, so that would generally be modern carbon cycle. Nuclear's got a reasonable little bit. Hydro's got quite a small part. And wind and solar, as of now, are pretty tiny. Okay, so turning to methane in the atmosphere, it's both a well-mixed greenhouse gas and a near-term climate forcer. So it's a stable enough molecule that it gets well spread through the atmosphere. So presently it's about 1,800 parts per billion, and it was 700 and a bit in 1750. And you can measure methane anywhere and you've more or less got it. anywhere in the atmosphere. NASA's Earth Observatory website shows a nice plot with a bit of a gradient of methane from northern hemisphere to southern hemisphere. But they've carefully plotted it starting at about not 1750 years, but maybe 1700 parts per billion. So if you start to plot at zero, there isn't much gradient of methane through the atmosphere. And according to assessment report 5, it has a half-life or a lifetime of 12.4 years. And that's long enough to get well mixed around the atmosphere. And the main mechanism of its removal from the atmosphere is reaction with hydroxyl groups. And because it's a well-mixed gas, every methane molecule in the atmosphere has an equal probability of meeting a hydroxyl group and therefore ending its radiative forcing career. And the number of reactions between methane and hydroxyl groups must be proportional to the number of methane molecules in the atmosphere. And so my gut instinct tells me that dm body T equals Kn ought to be a reasonable approximation. And I would just add on this that that's pretty much what happens or it's the same equation as happens in radioactive decay, but it's not, the process is kind of fundamentally different because in this case, that half-life is a property of both the gas and the atmosphere. So at present, the way that methane is removed from the atmosphere is such that it has a half-life about 12.4 years. And that's a function of the atmospheric chemistry that prevails now. And if we were to, for example, double the methane concentration, well, I think the 12.4 orbits would be off on the 12.4 years. You could expect some different lifetime to be the case then. And as for what M is, well, M is a particular group of methane molecules or a particular 100 tonnes of methane. It could be 100 tonnes of methane that's already up there, or it could be 100 tonnes of methane that we put up there tomorrow. Once it's a methane molecule in the atmosphere and has had time to get well mixed around, well, they're all the same. And you can take any particular subset of the atmosphere's methane and it will all behave according to the 12.4 year half-life. So I hope that makes a moderate amount of sense. And as everyone will remember from their high school maths, that differential equation integrates up to m equals m naught e to the kt. And k is less than 0, so we have exponential decay. But the problem with this is it's only half the story. And what's really going on up there in the sky is this: dm body T equals km plus r of T, with k less than 0 but r more than 0, and r is the rate of emission of methane. And so in words, what it means is the amount of methane in the atmosphere depends on the balance between removal and emission. And indeed, whether the mass of methane in the atmosphere is increasing or decreasing. Now that differential equation with R of T included doesn't have a nice, tidy analytical solution, but it's not a problem because it's very easy to model in a spreadsheet. All you have to do is pick a time step, and at every time step, you add some gas and take some gas away, having started with an initial mass of methane. And so in the spreadsheet model that I've done, I extend in 1 day time steps from 1990 to 2050. And there may be arguments for larger or smaller time steps. In saying that the radiation back to space has to occur at 340 watts per square metre. There's, of course, a time and space averaging involved in that. So the Earth gets colder at night and warmer during the day. So, and from that point of view, one day might be a shortish time step. But I don't think the process would be very sensitive to time step. So what I've done for my methane model is to calibrate the decay constant by comparison with figure 828 of assessment report 5. And I've interpreted the meaning of lifetime by reference to figure 828. And then I've repeated it for a 12.4 year lifetime of methane. So figure 828 was a 13-year lifetime. So I've adjusted the function for a 12.4 year lifetime. Then for R of T, as it were, the emissions function, I've used the New Zealand Greenhouse Gas Inventory and the Climate Change Commission's draft advice. And then I've modelled, starting in 1990, the mass of methane in the atmosphere. First of all, having to estimate what the initial mass was. I can show how that's done, and I think it can be done reasonably well. So here is the decay of mass of methane, and I've chosen to decay 85 tonnes or 85 kilograms or something. The reason will be obvious shortly. And I have adjusted the decay constant so that it agrees with figure 828 of assessment report 5. And so what you see here is figure 828 overlaid with the blue curve that I just showed. And so my time scale has been stretched to somewhere near agree with the time scale of figure 828, and my mass time scale has been adjusted to agree with the radiative forcing time scale of figure 828. So I make the assumption that the radiative forcing is proportional to the mass of gas. And I think this is clearly implied by assessment report 5, because they report radiative forcing per kilogram. So what I get from my spreadsheet, which is not so easy to read directly off the figure. So what I want to note there is that there's my blue curve agrees pretty well, and this is the one with a 13-year half-life, adjusted to agree with that 13-year half-life. It agrees acceptably well. And there may be some technical hitches in that, because I didn't quite manage to scan the figure 828 quite square to the page, and the adjustment of my figure, the angular adjustment that you get in Word to line up things wasn't quite fine-grained enough to get them lining up perfectly. So, but what I think is that the people at Working Group I are pretty much in agreement that exponential decay represents the way that methane is lost from the atmosphere reasonably well. So that blue curve that had a decay constant of 0.00195 per day, and reading off my spreadsheet, 39.6% remained at 13 years, and that was apparently the measure of the lifetime. And I don't know why not 50, but... And so what I've done is to create another curve with a 12.4 year lifetime, such that 39.6% of the initial mass remains at 12.4 years. And that has another slightly larger decay constant, 0.30205. And for the methane emissions, so in 1990, the greenhouse gas inventory says it was about 1291 kilotons, and a bit more than that in 2016. And then in 2018, according to the CCC draft advice, pretty similar, around about the 1300 kilotons. And then the next two are what the Climate Change Commission proposes we should aim for: 1206 kilotons in 2030 and 848 is the middle of their range for 2050. So I used those to define R of T, the emissions of methane, as a function of time. So this, the green curve is the annual emissions. So it shows the emissions as estimated by the greenhouse gas inventory, followed by the change as proposed by Climate Change Commission. And the red curve shows the results of the methane model, the spreadsheet model, assuming that there were 17,000 kilotons at 1990. So there's been 30 years during which we know our methane emissions, and compared with the lifetime of 12.4 years. And I understand the medical guideline is after 5 half-lives, you can forget about the amount of the initial drug or whatever. So, in looking at figure 828 of AR5, something similar, after 60 years, what you started with wouldn't matter. It would only what you input to the atmosphere over the last 60 years matters. So what I'm guessing is that up till 1990, we had a gradually climbing methane emission, and it's been moderately constant since then at about 1,300 kilotons per year. And so I reckon that you would expect under those conditions that the mass of methane in the atmosphere due to our New Zealand activities would be about constant. And so that was the basis for choosing the 17,000 kilotons of methane at 1990. And I would say, if anything, I've slightly underestimated it, because on having that fairly constant rate of methane emissions, the methane mass is climbing slowly over those 30 years. So what would it mean? So in a way, that was the main point of this talk, is I reckon we can estimate reasonably well the mass of methane that we keep up there in the sky. And the next thing would be to follow on from that. What does that mean in terms of radiative forcing? And so this is figure 829 of Assessment Report 5. And the black curve is the global warming potential of methane as a function of time. And over that first little interval, say the first few years, you've more, and you put up your 1 tonne of carbon dioxide and your 1 tonne of methane, and over those first few years, you've more or less got the same masses of both of them. And so you'll recall that absolute global warming potential is the integral of RF to T. And so over that short little interval at the start, before we've lost too much mass, the ratio, the GWP curve indicates the ratio of radiative forcing. So radiative forcing per kilogram of methane compared with per kilogram of carbon dioxide. And looking at that, I mean, for a rough figure, you could say that methane has radiative forcing effect about 100 times that of carbon dioxide per kilogram of the gas in the atmosphere. so that's what I've said there. And this is a quick rough calculation with some fairly rough and ready figures. The annual long-lived greenhouse gas emissions in 2018 were about 40 megatons of carbon dioxide equivalent, according to the CCC. And therefore, I say that the radiative forcing due to those long-lived greenhouse gas emissions in 2018 were 40 units, some kind of an energy input proportional to the mass of carbon dioxide equivalent that we put up there. So I'm just saying 40 units. And from the mass modelling, I estimate that there's 18 megatons, 18,000 kilotons of methane in the atmosphere in 2020 due to our New Zealand emissions of methane. And they are about 100 times more effective than carbon dioxide. So let's say there's 1,800 units of radiative forcing due to the methane that we maintain in the atmosphere. And if you divide that, you get 45 years. So the mass of methane that we keep up there has equivalent radiative forcing effect to about 45 years of our present day accumulation, of our long-lived greenhouse gases at our present day rates of emission. And that seems somewhat significant. And I don't really claim that that would be the last word on what the numbers would be. I'm aware that there would be other ways to calculate the ratio. But the main point, I think, is that we can estimate in that way, and we can say that we can have a more like an apples for apples comparison of the radiative forcing of our methane compared with our other gas emissions. Hang on. Okay, no, it's not right. That's better. So there's a couple of other things it says in Assessment Report 5 about methane. It distinguishes between radiative forcing due to concentration and due to emissions. So if you operate the line-by-line codes, as I believe they're called, and based on the concentration of methane in the atmosphere, you come to the 0.48 watts per square metre of radiative forcing increase since 1750. But it's a little more complicated because when you increase the methane concentration in the atmosphere, you decrease the abundance of hydroxyl groups. So there's some kind of an equilibrium reaction going on there, and the more methane you put up there, the less hydroxyl group concentration you have. And that reduces the rate of removal of methane. Chapter 6 of AR5, and also I've just realised Chapter 8 of AR5, say that they describe the chemistry by which hydroxyl groups are produced. So there is quite some buffering capacity too. It's not like there's a finite amount of the stuff and we're gobbling it all up by putting up methane. So that's one thing, that you remove or you reduce the ability of the atmosphere to clean out the methane. And the other things are that emitting methane leads to some ozone production and some stratospheric water vapour production, which both have a radiative forcing effect. And so Assessment Report 5 says that if you take those other things into account, the radiative forcing due to methane emissions could be something like double, 0.97 watts per square metre. So in conclusion, I would say that methane removal from the atmosphere is reasonably well approximated by exponential decay. And therefore it's possible to estimate the mass of methane that is maintained in the atmosphere by a given time series of methane emissions. So you could do it for the whole world, or you could do it for New Zealand, or you could do it for your local landfill. And the mass of methane in the atmosphere due to our New Zealand emissions is equivalent to, well, I reckon it's probably going to be some decades accumulation of our long-lived greenhouse gas emissions. So that's all I had to say. And I'm happy to try and answer any questions.
Yeah, thanks very much, Hugh. A lot to ponder there. And since we're a reasonably small group, I think we can probably handle people just unmuting themselves and asking a question if they have one. So it's just gone 7 o'clock, and I think maybe we aim to have sort of 15 minutes of questions, and then I'll interject at that point and see if Hugh's had enough. So yeah, if anyone wants to jump in with questions for Hugh, go for it.
Greetings, Hugh. Can you hear me? David Painter.
I can, David. Yeah, great to hear you.
And I have not read chapter 6 and chapter 8 of AR5, but I'm intrigued to know what governs hydroxyl concentrations in the atmosphere other than the interaction with methane.
I just read it tonight. There are a couple of reasons why it is produced. I'm afraid I can't remember off the top of my head.
No, that's okay. You probably get the impression that I'm interested to know because are there other things happening which are changing the concentration of hydroxyl at the same time as we are interested in methane?
The one thing I've heard about is from Jim Salinger, and he said that afforestation was possibly a risk for our climate future because the volatiles which forests put into the atmosphere tend to reduce the concentration of hydroxyl groups.
Right. Yep. Thank you.
Steve Goldthorpe here. I've just thrown up a graph on my screen. I just Googled global methane concentration. And what this graph shows, which is something from Nature, so presumably it's fairly realistic, it's a graph from 1984 through to 2020. And it shows methane concentrations growing from 1600 to 1700. And around 2005-06, leveling off at around 1800. From 2006 on, it shows the methane concentrations in the atmosphere starting to increase again up to nearly 1900 now. And I'm just curious as to what the mechanism might be that methane was rising through to the early 2000s. Was sort of stabilizing and then has taken off again and is increasing at the same rate as it was prior to 1990 as we go up towards 2020. Any thoughts from anyone about why that might be the case?
Well, on my side, I have to say I don't really know. I mean, I know that I think leakage from natural gas production is a pretty significant source worldwide. No, I'm afraid I can't help. Does anyone else know?
I would have thought that you're right, that natural gas leakage is probably more significant than is reported or could be on the basis that the gas producers quite rightly are focused principally on safety, and one of the main ways you make a gas system safe is to make sure it's well vented and that any leaks are dispersed, and that it's very difficult to actually measure what those are. You just want to make sure that it's safe and doesn't go bang. But also I'm wondering whether beyond sort of from say 2005, 2010 onwards, there's been a lot more fracking going on. I did some studies back in 2011 about fracking and the greenhouse gas emissions from that, and they were quite significantly greater than ordinary gas production. So I'm wondering whether that might be a reason. And indeed, as far as New Zealand's concerned, the methane emissions from oil and gas production that are reported to the ministry, I'm wondering to what extent we can be confident that they're accurate.
Interesting.
Steve, I'd be very surprised if the individual fracking operations had anything like the magnitude of the natural processes, some of which are changing with increased temperature anyway, which is methane production from the beds of water bodies. People are talking about permafrost melting and releasing methane, and those are over some huge areas, whereas the fracking is virtually a point source.
Yeah, I mean the reason for this increase since over the last decade or more could well be from permafrost, which we see reports saying that it's unprecedented is usually the term that's used.
Hugh, we've got a question arising from the chat, someone from a non-scientist background. And I think coming through in your talk, it showed how, carbon dioxide stays in the atmosphere more or less permanently, if you want to approximate it, but methane sort of decays over time. So from that perspective, you could say it's a lot less detrimental to the climate. But I think, would you care to comment, Hugh, on the ways from your talk that methane is perhaps considered more detrimental to the climate than CO2?
Well, I think, I mean, the main, well, I mean, in some ways, methane is a good thing to have, because if you stop putting it up there, then there will soon be less of it. If we could restrain our sources, then we can kind of get ahead on that one. I guess the main point I wanted to make is that I think we are. I think the official half of our greenhouse gas profile due to methane is. I don't think it's. I think it's more than that, really, when you consider that it could be some decades of our other gas emissions. Hope that's something like answers the question.
Can I have another one before I go back and resume my dinner? Hugh, I have found this very interesting, and I congratulate you on having some original thinking going into it. I wonder, what are you going to do with this next? Are you going to fly it by one of the conventional climate scientists in New Zealand, or are you going to publish it?
Well, I did have a proper climate scientist give it a review, and he was kind of sniffy about my methods, and he thought I should be getting into triple CFs, which is a coupled carbon climate cycle feedback model. And I had a quick look at a paper or two, and I thought, no, there's a career in that.
Yes.
So I thought, well, I don't have another career to spend.
Right.
And it did go into something like this argument did go into our ESR submission to the Climate Change Commission's draft advice. And I feel that if other people think it's a relevant, useful switch of perspective, then I think it probably needs a proper professional in the area to look at it and maybe put some better numbers on it. There's one kind of strange thing, and that's that that ratio of 100 odd, that doesn't seem to stack up with the concentrations of methane and carbon dioxide in the atmosphere and their relative radiative forcings. I don't really understand that. I don't know. I don't think I have a career to spend on it. I don't think I'm going to publish it. I don't think I can't see that a peer-reviewed journal would accept it. I think I just put it out there as an idea, really.
Okay. Well, it's back to dinner for me, but hey, thank you very much, Hugh. I've enjoyed sitting here with my glass of red wine and listening to you, and good to see you again. So bye for now.
Thanks, Dave.
Hugh, could I just ask a quick question, which is sort of similar to the one that Brendan put forward, which is, if we had to translate what you've said into a message for a politician, what would that message be? Is there a message there? Is it at a stage where you could give a politician a simple message?
Well, I suppose I think that the message is that our methane emissions are, well, here's a go at a message for a politician. Our methane emissions mean that our radiative forcing profile is dominated by methane. It's by far the most important thing. The fact that it's methane is an opportunity, because if we reduce our methane emissions, we reduce our contribution to global warming over a relatively short time frame, like in 20 years, if we significantly reduce our methane emissions. And I suppose one would have to say something about ruminants. Ruminants might be the next thing on the horizon, and that's politically very difficult, of course.
Yeah.
I understand, I think, from Eric Turnsmeyer's book, The Carbon Farming Solution, that humans and their food animals are by far the greatest part of mammalian biomass. And I feel that that we should be looking at, if we're looking at feeding humanity, then we should be looking at a rational way of doing that. And that won't necessarily mean an awful lot of meat. In fact, I think it would probably mean less meat. And so I guess I would be asserting to a politician that the world could be run differently. I don't know, I'm not. And that it could be a satisfactory world, even if it were run differently.
Hugh, Jack Woodward speaking. I don't think I've followed in detail what you said, but I think it does speak to a concern that I have over the methane emissions and concentrations in our atmosphere, that the present procedures, mechanisms for including them are not satisfactory, and they do tend to rather downplay the importance of methane. That's, I'm afraid, it's more of a gut feeling of that the right thing to say about methane. But I think that I'm thanks very much for your analysis. I'll go back to it and I'll think about it. Thanks a lot, Hugh.
Well, thanks very much for those thoughts. That's exactly what I thought. It just seems unsatisfactory, the GWP 100 or even the GWP 20. And I think the problem is that people, and maybe for very good reasons, have tried to focus on emissions. And I think it would be more useful to go the next step and focus on radiative forcing, which is what's really doing the damage.
Yes, well, I second that, Hugh. I think you've expressed the discomfort that I feel with the way that we're treating methane emissions at the moment.
Great, music to my ears.
Hugh, just to bounce a comment off you, it seems like perhaps that 100-year horizon that they average the methane emissions over almost kind of reflects the kind of time frame that people had in their minds, say at the turn of the millennium. They sort of thought we've got 100 years to deal with the problem, and what proportion of the problem is methane and what proportion is carbon. But now we've kind of progressed and realized that we need to do it a lot faster, and it seems like it does call into question those timeframes as being a bit arbitrary and not in line with the urgency of the task. What would you comment on that?
Yeah, I agree, and it may well be because of that. There's a piece in chapter 8 where they quote the original proposer of the GWP, and he says there is no scientific justification for choosing any particular time horizon. Whatever you choose, you are still not really going to be comparing apples with apples, because and I think as far as I can see, the only way you can is by calculating the mass of methane in the atmosphere and comparing that with the mass of carbon dioxide that we're continuing to put up in the atmosphere. And I think, to put it in the shortest possible mathematical terms, where the current metric goes wrong is that it looks at pulses and it doesn't look at a continuous function, and it leaves out that term R of T, the rate of emission of methane.
Thank you. I'm leaving now, but thanks a lot for your presentation.
Thanks for coming.
Yeah, it is just about time that we wrap things up. Does anyone have one final question for Hugh? Well, if not, then Hugh, I just want to pass on the fact that on the message board, there's been a number of people saying thanks very much and for a really interesting perspective. Thank you very much for all the time and effort you've put into preparing the presentation for us today.
Okay. Thanks for the opportunity to talk about it.